All right, we're going to go ahead and get started. We are pleased to have Dr. Keith Schilling here with us today. Dr. Schilling is the state geologist and research engineer at the Iowa Geological Survey at the University of Iowa and an adjunct assistant professor at both the University of Iowa Department of Earth and Environmental Science and at Iowa State University Department of Natural Resources, Ecology, and Management. He received his master's degree in water resources from Iowa State University and a PhD degree in geology from the University of Iowa. His research has focused on a variety of water-related issues in Iowa, including groundwater flow and quality, surface and groundwater interaction, non-point source pollution, and watershed and floodplain processes. Please help me welcome Dr. Schilling.
Okay, in the back, is this okay? Excellent. Well, it's a pleasure to be here. I was just saying that I think I know at least a fraction of you from different projects and new interactions today. So it's like, keep this as conversational as you want it to be. If you have any questions or something that come up, feel free to interrupt in the process. So starting off with a little bit about me and who I work for. I work for the Iowa Geological Survey. We're 126 years old as a geological survey located at the University of Iowa. We're now reside in the College of Engineering at IIHR at the University of Iowa. We're about 10 people strong with hydrogeology and geology folks, bedrock and quaternary geology. One of your alums from the Groundwater department, Matthew Streeter, is up in the top part of that photo. So, you know, there's potential for all of you at some point. So we do a variety of different things across Iowa, focused on geology and groundwater services. So know that we're available to work with just about anybody on anything. We're mostly state funded, so we have some flexibility to do a lot of different things. Okay, so why am I here? This is maybe something a little bit different. This is more of a groundwater talk than maybe what you're used to. Groundwater monitoring is done, but it's really never really done at a landscape scale or a statewide scale. It's typically done very project specific, very little connectivity between one site and another. There was a handful of USGS wells that were installed across the state for some long-term monitoring. Our University of Iowa Iowa Watershed Approach project has put in a handful of other wells across the state, but otherwise, water level monitoring is not often done in Iowa. But the water table is something I think worth monitoring because it integrates a lot of processes. So from precipitation, recharge into the aquifer, we get processes associated with soil moisture. We can infer some processes there based on how the water table behaves. We can look at groundwater recharge. The R is recharge into the water table. We can look at evapotranspiration from the water table, and we can use the water table as a indication of deep groundwater flow and recharge to deeper aquifers. So monitoring the water table really has a lot of intrinsic value, not just from the simple monitoring of it, but what you can infer about a lot of other processes, because it really does integrate a lot of different things. So what am I going to talk about today? Well, this is want to focus on a couple of processes that the water table monitoring does integrate. First off, I'm going to talk a little bit about how to use water table monitoring to say something about crop evapotranspiration. Then I'm going to move to how does groundwater behave along a transect, a hillside transect, and then develop this concept of groundwater response units that I've kind of been exploring lately and provide some examples from different projects I've been working on the last couple years. So how do we use water table monitoring to infer some things about evapotranspiration? Well, we've had a project for the last 10 years I worked with a colleague from Grinnell College, Peter Jacobson, on a preserve, Swamp White Oak Preserve. It's a floodplain of the Cedar River, kind of by Conesville. Just an absolutely beautiful place. There's a stream. There's our site here with some monitoring wells in the Cedar River right there next to the at the Conesville gauge, USGS gauge. Absolutely beautiful place. It's one of these rare ecosystems of a sand prairie on this floodplain setting. Just absolutely beautiful. Well, we put monitoring wells. We have monitoring wells in the floodplain, and also looked at stage increases in the Cedar River. And it's pretty clear that they track along very closely together. If we zoom in on one little peak, you kind of see how the stage in the Cedar River increases over the course of an event, and how the floodplain water level responds along with it. What's interesting, though, is you see these little squiggles. We lose them a little bit when the stage increases, and they pick up again. Well, those rising and fall behavior, that water table, is essentially related to the plant evapotranspiration. So the plants transpire to the day, they lose a lot of water through their leaves and the stomata that are open. We get drawdown of the water table, they close up at night, we get recovery. And you can use the diurnal fluctuations of the water table to estimate plant evapotranspiration, at least the ET part that's coming from groundwater. You look at how much the level of decrease during the day and what the recovery rate is at night. Those all relate down here. You multiply by the specific yield, and you get some idea of what ET is. The nice thing about doing something like this is you get a chance to get a daily value. You put all those days together, you kind of get a sense for how ET varies across the season. For this floodplain savanna, it was interesting just to see how over a course of a year, you add up all those daily values and you get about 400 millimeters of water uptake from that floodplain savanna per year. You add all that up in terms of a 300 hectare or 150 hectare preserve, it's equivalent to a well pumping 300 gallons a minute at that floodplain. So estimating something like this is important by doing any sort of water budgets and so forth. We need to know something about how much evapotranspiration might be occurring from some of this vegetation. Another example of ET was some work down at Walnut Creek in Jasper County at the Neil Smith National Wildlife Refuge. I put a series of wells here in the floodplain from a crop system, some woods, and then a reed canary grass area. You can kind of see again here where we have fluctuations that occur, water table rise and then recession under grass, corn, and woods. Without getting into great detail, there's other work that's been published from that, but it's interesting. You got these kind of diurnal patterns under the forest, and what I was observing was more of a step pattern in the grass and the corn. And what was more unique about it was just doing this ET thing on an hourly basis. You kind of see when the plants start transpiring, we got a big change in water table level during the day, closed up at night, and you kind of see how the seasonal response kind of diminishes. So that's this idea about maybe using water table monitoring to estimate some things about ET. Moving on along towards groundwater recharge. We've had another series of wells that we put along a hillside in Walnut Creek in Jasper County. There's a series of 4 wells here that span from an upland location to a floodplain. So leaving behind a lot of the details because I want to get to something a little bit more current. But in this case, we had the typical stratigraphy that those have moved off the Des Moines lobe here at Iowa State University would see, is that we have a loess and kind of oxidized glacial till over a hill slope largely composed of unoxidized pre-Illinois till. We have upland, side slopes, and a floodplain with wells associated with that transect. Groundwater flow, of course, is down gradient, downhill, following that topography. And throwing out all the details about how I got to this spot, But in general, after doing this study, what we found is that the amount of precipitation that makes it into groundwater recharge varies considerably across this hill slope. So in the upland location, 24% of the precip in any given year makes it as groundwater recharge. A lot of it actually gets captured in the soil moisture term. So we can infer some things about soil moisture because of this ratio. In the slope area, only 14% of precip makes it to the water table because a lot of it is running off. And in the floodplain, we get more concentrated recharge occurring in the floodplain, where 44% of precip makes it into there. Mainly because we have contributions of runoff, we have groundwater flow, we got surface and groundwater interaction, plus the rainfall. The water table is much shallower, there's less captured by soil moisture there. Okay, let's move on to the groundwater response unit ideas. I mean, a lot of you here have probably worked with SWAT. It's a soil water assessment tool, common watershed models, watershed model. And how SWAT works is you take, divide a watershed into subbasins, you have a land cover term, a soil type, a slope class, and you integrate all these on a certain hydrologic response unit basis. And you add up all these individual pieces, and you get the watershed response. Been very successful, thousands of studies out there using SWAT for watershed models. So my thought is that we could probably use the same kind of concept and think about in terms of a groundwater response unit. Based on some of the work I just talked about, you say, okay, what's the land cover in a part of a watershed? What's the landscape position? We just got done seeing that the difference between uplands, slopes, and floodplains matters a great deal. So where's that land cover? What's the landscape position? Then we need to estimate how much groundwater recharge occurs. And you combine all those together, and we have something about at least the water flux into a groundwater area. We add up all those water fluxes in the groundwater, they would be equivalent to what base flow is in the watershed. So how do we measure recharge? I've talked about it a little bit, but in general, if you look at a water table, you do high frequency or water table monitoring, you see that it rains, you see a groundwater rise occurs. Okay, so you have some level of groundwater rise. This is on a monthly, this could be a day, it doesn't really matter. Rainfall happens, we get a water level rise. Okay, now we're not necessarily filling up a meter of water on in a water table situation. We're only filling up the voids in the aquifer. So that's where the specific yield comes from, which is essentially how much of that aquifer void space is available to fill with water. So we multiply the water level rise, this delta H, by specific yield, and we say something about how much groundwater recharge occurred to cause that water level rise. You can estimate specific yield through soil tests and a variety of other mechanisms. Here's a paper that was done in published in WRR in 2005 from Steve Lohide, who's now at Wisconsin, and they did some modeling and developed this nice little handy textural diagram that shows what specific yield might be based on the texture of your material that you're dealing with. So in any cases like this loam texture, we're at about 0.04. Now it's a little bit lower than what you might think about specific yield. This is like readily available specific yield. So if it rains, this is the response that we see based on that. That's not completely wetting and that's not completely drying. Okay, so it's a little bit different, but this is the specific yield you use to convert the water level rise to recharge. So how does the water table vary across Iowa? You know, we were chatting about this earlier today. So clearly, water tables vary quite a bit. They vary seasonally. They vary with landscape position. So in this setting where we're by a glacial lake, like Okoboji, we see the water table next to the lake being relatively subdued. Okay, we're anchored by the hydraulic head in the lake, and we got less water level fluctuation there. Compared to the upland, where we see much larger water level fluctuations. So all water tables are not fluctuating the same way. There's clearly a slope component here, or a landscape position component. We see the same thing in a watershed. So this is out of Neil Smith for a different study, but we see the same thing where we see a very narrow range of floodplain water table fluctuations in one area compared to the upland areas, which might fluctuate 3 to 4 meters in any given year. Okay, so we have water levels behaving quite differently based on the landscape position that you're in. Okay. So if we want to say something about loading rate, though, we need to say something that's the water flux. We're going to get groundwater recharge from the water level rise and the specific yield. What's the concentration can we pair to that to get some idea of the nutrient loading? Well, one of the assumptions I made in this process is to say that the water table concentration is associated with the recharge associated with that through the soil profile. You know, we can probably debate that assumption, but that's sort of a simplifying assumption. We did some lysimeter work out at Neil Smith, and there's a pretty good relation between groundwater phosphorus in a lysimeter versus what's in the well. Okay, so we're saying that the soil, the water entering the water table is essentially the water quality of recharge. We've done other monitoring in farmed wetlands across north central Iowa, and what it does show is that the water table concentrations that we see are not static. They fluctuate quite a bit with when recharge happens. So kind of getting this water, the quality component to add to the flux of the flow itself, and you kind of see how we could estimate nutrient loading this way. Interestingly enough, the scale goes over 100 milligrams per liter. We had 102 milligrams per liter of nitrate with recharge after the 2012 drought here in this well. That was a record for me. I'd never seen a concentration in water table that high. But you got to see again how dynamic this is. Every time it rises and falls, we see the water quality at the water table changing. Okay, so let's apply that a little bit to some examples. One study we did the last few years was a reconnaissance study of Iowa golf courses. We had some funding from the Golf Course Superintendents Society of America, Iowa Turfgrass Association. As a group, they were interested in to say, hey, we keep getting lumped in with all this non-point source stuff, the nutrient reduction strategy. What are golf courses contributing? So we got some funding to put some wells in 6 different courses across the state. It's quite an interesting process to go drive a big old heavy drill rig out on a pristine golf course, but that's what we did. So we put wells in tee boxes, in the rough, and the fairway. You know, this was a country club up in northeast Iowa, just an absolutely beautiful place to put a dirty old monitoring well in. Anyway, so the idea was we had these golf courses, we put some wells in. They want to know what the concentrations are, and we want to know how much nutrient loading we are associated with these courses. First off, we put transducers in a well per course and can measure the water level fluctuations there. Courses varied, water levels varied quite a bit across the state. In the West 18 course was in the deep lust. The water table is average water table is 18 feet down. You get on the Des Moines lobe, the central 9 and 18 courses were at 3 feet down. So water levels varied quite a bit. Kind of see how those fluctuations occurred. And again, we can use these water table fluctuations to estimate recharge. Interesting, nitrate concentrations. I should have took a poll before we did this, but how do the concentrations look like in Iowa golf courses? They're very low. Okay, if you ask them, they say these courses, what they are is they're a professionally managed cover crop. That comes from the course superintendents. So they're very confident in their levels. They were very happy to have us come out and study this thing. So the average nitrate concentration was 1 or less, and like 3 of the 6 courses, we had 1 high concentration here in the deep lust in western Iowa. So we have the flux, we have the concentration. What are the loading rates? Multiply the concentration by the groundwater recharge, and we get what is the loading to the water table. So for these courses, you kind of see these are the average concentrations in the wells. This was how much groundwater recharge occurred. You multiply them across, and these were the loads in kilograms per hectare that we saw. It averaged of about 3 kilograms per hectare on the golf courses. So they were very pleased to see these kind of results compared to the watershed. So if you compare what the watersheds were producing compared to the courses themselves, you kind of see that the courses here averaged about 3. The river yields and the watersheds they were draining into were about 30, and we're about essentially 10% of the course. The courses are producing about 10% of what the watershed was producing on a load rate, yield rate. So interesting news that you can share to all your friends. Golf courses are not the nutrient source that people think they are. So what are some examples of this groundwater response unit idea? We have 3 examples from Okoboji. Clear Creek is a watershed in eastern Iowa, and then Walnut Creek again, looking at some orthophosphorus loading. Okoboji is Iowa's Great Lake up in northwestern Iowa. Through a project a few years ago, we put in a network of 22 wells across the watershed with the idea being to characterize the groundwater nutrient concentrations and how do they discharge and how much of that load is discharging into the lake. You know, clearly they want to prevent that lake from becoming impacted by nutrients. It's a humongous tourist destination. So we put transducers in a lot of locations. You can kind of see what we said before. You know, the lake shore was less fluctuation on the upland areas. We had more fluctuation. This was interesting. So I commandeered a well from an underground storage tank investigation that was installed under pavement. It's pretty clear we don't get a whole lot of groundwater recharge occurring under pavement. Okay, so I find that, you know, kind of interesting for folks to consider that you don't really see that. So combined with the concentration measurements from a cropland, averaged about 9 residential areas, golf course. So we developed this whole, again, this HRU, groundwater response unit basis, where we had the concentrations that we measured under these represented land covers multiplied by the groundwater recharge from the monitoring wells. And you kind of come up with, again, how much of that loading in that watershed area was coming from different land covers. So in this case, concentration, recharge, load per unit area, multiply that load per unit area by how much of that land cover is associated with the area, and you get a sense for how much of that load is coming from different land covers. So not a huge surprise to anybody here, 92% of the nitrate load to the lake was coming from row crop areas. Not a huge surprise. Interesting, again, the golf courses were very low, not that I keep picking on that. Clear Creek watershed. It's 275 square kilometers in eastern Iowa. It drains into Coralville and Iowa City through Tiffin. So for this watershed, we came into it thinking about this groundwater response unit idea. So we didn't have money to dot that watershed and put wells every, uniformly across the basin. So what I did was focus in on some dominant land covers there and said, all right, we want to represent the land cover and the landscape position classifications, and then we'll scale it up to the watershed scale. So land cover in Clear Creek, we divided into 4 categories: row crop, perennial, urban, and suburban, because we picked up Tiffin and Oxford here, suburban areas, less densely urban as the Iowa City Coralville area. Put water level transducers. So we're characterized 275 square kilometers with 13 wells. Okay, this is one idea about how we can we can use this kind of approach to scale up groundwater monitoring at a watershed scale. We had water level fluctuations here in the side slope, and the floodplain in the upland was much deeper water table depth. All kind of behave similarly. This is just a box plot of the different land covers, and we had deeper water tables under the uplands, and usually they kind of, depending on where you were, whether the slope or the floodplain, where they were on the water level fluctuation path. Again, we have similar stratigraphy as we had in Walnut Creek that I showed earlier, with oxidized loess and till over on oxidized prealluvial till and alluvium. So we had one side slope well, one upland well, and a floodplain well, and that was the proportion of annual recharge that we got based on this water table fluctuation method. So the floodplains, again, were the source of concentrated recharge. Uplands were less, and the side slopes were less than that. So again, we see patterns of recharge occurring on a watershed based on the slope and so forth. So way too much, so I'm going to highlight some things, so don't get scared by this. This just shows, again, what this shows is based on the upland, side slope, or floodplain location, what was the recharge, what was the loading rate, what was the fraction of the annual watershed total that was associated with these different groundwater response units. For example, we saw greater nitrogen loading in row crop areas and in floodplains more specifically. So again, like Okoboji, in this case we had 96% of the nitrate load in the watershed coming from row crop areas despite occupying 57% of the area. Okay? Phosphorus loads. Phosphorus loads were a little more evenly distributed. This is groundwater phosphorus, not total phosphorus exported. Essentially 53%, a little more proportional to the land area. In general, we just do not see a lot of variation by land cover or slope class in phosphorus that we do in nitrate. So a little more evenly distributed. We also had chloride. So we had high chloride concentrations and loading rates associated with urban areas and de-icing and suburban road salt. So from this study, we were able to kind of partition how much the loads were coming from what land covers and where. So if you want to do any sort of non-point source targeting, this is some mechanism to identify where some of this is occurring. All right, last example, let's go through Walnut Creek again, and now we're going to look at groundwater orthophosphorus concentrations, the mass and distribution. So you're starting with the watershed, you want to monitor for your pollutant of some sort. How do you do that? Here we had a network of 12 monitoring wells per 20 square mile watershed. How do you use only 12 wells to characterize this watershed? Again, it's the groundwater response unit idea. Our objectives were to kind of quantify the spatial patterns, identify some major controls, and quantify the mass of orthophosphorus that might be in shallow groundwater in the watershed. From our network of 12 wells, we divided them up either in upland. We kind of skimped on the side slope, so we put them in either class of uplands or floodplains. Uplands were anything that weren't a floodplain. Okay, but what you did see was differences in water quality conditions and water table depth. Deeper water tables in this box plot beneath the uplands compared to the floodplains. Higher orthophosphorus concentrations in floodplain compared to the uplands, and you can kind of see DO conditions and specific conductance kind of variations across the watershed. Among the different land covers, we saw higher orthophosphorus concentrations in shallow water table beneath the pasture compared to the woods. The warm season grass was somewhere in between, probably as much a legacy of historical operations as it was, restored prairie. We had a question about whether the orthophosphorus might relate to how many years since this area had been converted from row crop to prairie, because some of these wells were in restored prairie areas. Like I've shown before in other work, we do see deeper water tables I guess that's deeper water tables and older prairies. Interesting. It kind of fits with this greater water demand from prairie compared to seasonal crops, but no relation at all in terms of the orthophosphorus concentration based on how many years it's been since it's been restored. So what are the loading rates here? Again, concentration, quality water, and recharge. So we're able to estimate the loading rates. Here's just some of the network of wells where we had the recharge, the concentrations varied both years, and then we had the yield. Okay, summarized up here in this diagram. So the upland areas had a loading rate of about 0.11 kilograms per hectare, and the groundwater concentrations were a little bit lower. The floodplain groundwater concentrations averaged, again, 0.11 milligram per liter, but we had about 3 times as much recharge. So we had a lot of concentrated recharge occurring in the floodplain, generating with these higher concentrations to say that we had perhaps higher loading rates associated with the floodplain. Kind of consistent with what we've seen before, we do see a lot of greater recharge occurring on floodplain areas compared to other landscape positions. So how much orthophosphorus mass is in the watershed? That's where some of these mechanisms to total these things get kind of interesting, because you could say, given the yield and the loads associated with these land cover areas, we have the area of floodplains, we have the area of uplands, times that kilograms per load, we can say something about how much mass of orthophosphorus might be in the water table, or at least the water table above the pre-Illinois till. So here we had an area-weighted loading rate to groundwater based on these landscape positions. So in 2015, we had about 918 kilograms of orthophosphorus enter the water table, and we had export of orthophosphorus with base flow at 500 kilograms. The next year, crazily enough, it was the same. You know, given all the errors associated with this, that was hard to see that happening, but we had an equal balance that year. So you can kind of estimate a little bit about, are we adding orthophosphorus, or are we in balance, or whatever, so it gives you some idea of what is the mass balance of phosphorus in this watershed. If we could add up all of our area-weighted location, or floodplains and uplands, assume a 5-meter depth and a porosity of about 0.25, we had 530 kilograms of annual base flow of orthophosphorus. Given how much is there, it would take about 7.7 years, let's round to 8 years, to remove essentially the orthophosphorus that's being stored in shallow groundwater in the watershed. So I thought I was going to run out of time, but I think I'm right on schedule. Hopefully I haven't gone too fast or too slow for you. Conclusions. Hopefully I've kind of indicated that the water table monitoring, especially if we do it at a frequency greater than monthly or quarterly, we can infer some hydrologic processes associated with that. We can infer some things about soil moisture based on the response of the water table. We can say something about evapotranspiration if we detect a signal there, and we can certainly say something about groundwater recharge. All of these are important hydrologic processes in a watershed scale that we can get some clues about should we monitor the water table at a high frequency. Groundwater concentrations multiplied by that groundwater recharge gets you some idea of the mass loading rate to groundwater. You add up those groundwater response units at a watershed scale, you have something, you can say something about where those loads are being generated, and you add them all up in a groundwater response unit like the hydrologic response units in SWAT, you get some idea of what the non-point source loading might be in a watershed. Where is it coming from? How much is coming from certain areas? And finally, the point made for watershed, monitoring groundwater at a watershed scale is you use an approach like this, you can substantially minimize the number of wells needed to quantify groundwater conditions at a watershed scale. we do a lot of watershed monitoring of groundwater. You know, they tend to, like I said, tend to be site-specific. They tend to be really associated with a project here or there. This mechanism, this groundwater response approach, has a way to minimize that and still gain some valuable information about groundwater conditions. You know, if we're going to do a water budget or mass balance in a watershed, groundwater is an important component. So with that, I would be happy to take any questions. Yes.
Can you define groundwater for us? So like, for example, are tiles draining groundwater? Or are they above groundwater draining soil water? Is there a legal definition too?
Well, legal is a whole different ballgame. I'm not touching legal, but I would call groundwater is where all the soil pores, it's 100% saturation. So anything less than that, we're talking about water kind of held in tension in the soil profile. So in our farmed wetland study, we could see in some cases where the groundwater level might be 3 or 4 feet down, and we had ponded water above. That ponded water was not groundwater. That was ponded surface water that wasn't infiltrating the groundwater. 100% saturation was still much lower. So that's what I'm talking about. When we're talking about water in the soil profile, as a groundwater person, that's not groundwater to me. That's soil moisture. Oh, all in the back.
Question along the line of your first conclusion. Maybe you can elaborate a little bit more on monitoring the water table and estimating evapotranspiration. I'll just bring up 2 points. One, you mentioned it in your talk that by monitoring the fluctuations in the water table, maybe you can learn something about the contribution of water, groundwater or water table to evapotranspiration, but not the whole of evapotranspiration.
Right.
A portion of it.
Right.
But the second point is, it seems to me that because you're looking at the fluctuation, there's a decrease in the water table and then an increase. That this can only work, in my thinking, it can only work if you've got some kind of a surface water, some kind of a replenishing supply to cause the water table to recover. It's not going to happen everywhere, but it has to be at certain locations.
Well, I mean, I've been in different locations where this has worked. So the replenishment is where it's like a temporary decrease because of pumping. You know, the vegetation is pumping, so there's like a pumping well with a little bit of a depression. Then it shuts off and it recovers, and it only recovers. I mean, it goes down a little bit every day, but it's just a little bit, you know. So the way this, I could go back and look at it, but you'd see the scale on the left axis is really quite fine, you know. Like, we're not talking about inches or even feet, you know. Like, this is like millimeters of difference. So you need the equipment and the sensitivity of your pressure transducers to pick this up. But yes, you're right that this is just the groundwater component to ET. So in a paper or two where I've done this, it's like it's ET with a little G on it because it's just the groundwater part of this. I probably glossed over that a little too quickly. Yes?
I was curious, sorry I came in late so I might have missed it, but I was surprised by the amount of nitrate loading on the side slope too. I know you didn't talk about it a lot, but how did you capture the variability of the side slope? Because I think of, whether it's a dispersive or a convergent slope and how much that might affect the actual groundwater.
Well, those level of details was not captured here. So this is like in a general landscape position. So it's captured exactly the same way the other two settings were. So what is the water table fluctuation like? And that's saying how much water is entering the top of the water table. So the other flow components, the runoff component or other aspects of the nitrogen cycling, not included. So this is really about how much nitrate might be loading to the top of the water table in a floodplain environment. So probably a lot more simplified than what you're thinking. It's pretty simple.
How
barometric pressure fluctuation influence on the water table?
And these, there would be none because they're all vented transducers, so they're already equilibrated to barometric pressure. I gotta say, when you use non-vented ones, I'm not sure they're sensitive enough that some of those corrections, it seems like they kind of mess with that signal a little bit, because if they're not like on the mark, you know, that gets lost. So these were vented transducers, which made that a lot easier. Mike?
I was really surprised by the nitrate loading from the urban area or the residential areas. I guess in many of these areas, I understand now the topsoil is stripped and sold, and then they put the housing development in. How do you have any idea how that might affect the loading?
I don't. So in the cases here, we're pretty much going where the city and or an owner would let you go. So really no consideration at all given to that. But
do you have a rough sense whether they were newer or?
yeah, they were newer.
They were newer developments.
Yeah. Yes, Mike.
In the phosphorus study, could you go back to that slide with the 7.7? I remember that value. Yeah, the 7.7 years.
Oh, yeah.
So what does that, could you tell us a little bit more about what you mean by residence time there? And,
Yeah.
does it mean that that's the amount of time that phosphorus can stay in the watershed? Could that phosphorus be flushed out of the watershed? Under what circumstances? 57.7.
Yeah, that's a good point. So let's say we shut off the spigot and there's no more orthophosphorus being generated with recharge. Just to remove the phosphorus in the water table, based on these conditions, the upper 5 meters of the water table, it would take 7.7 years. It seems like, I don't know if that's short or long, but we've done groundwater travel times there, estimates in that watershed, where the average residence time of groundwater is about 10 years. So these are actually pretty equivalent to what any water particle entering into the water table in Walnut Creek, on average, would take 10 years before it discharged from the watershed with flow. So we're kind of on par with that, but this kind of gives you some idea of, say we're going to, shut it off, or we're going to reduce all orthophosphorus loading to the watershed. We're not seeing any differences in that orthophosphorus change until we start working on that 7.7 years. So it's kind of some back of the envelope idea on the time to see an effect. So we're going to take a while to see an effect if we're still generating orthophosphorus going through the soil profile, entering the water table. We're going to continue to see it because we can shut it all off and not see an effect in 7 years.
Thank you.
Mm-hmm.
Well, what is the likelihood of shutting off?
Like 0? Because this is, again, this is restored prairie, and I was chatting with somebody over lunch, and I've probably put in several hundred monitoring wells across the state in different projects, and more often than not, we're measuring dissolved phosphorus or orthophosphorus. There's pretty much nowhere I haven't seen it less than 0.07 milligrams per liter. This is like in sand, tallgrass, or prairie restorations at Okoboji, it's 0.07. Like in cropland, it might be 0.15. We see it everywhere at about this rate. So you see it there, and if you assume that that's equivalent or similar to what recharge would be, every time we're moving water through that soil profile, we're picking up phosphorus to generate that kind of concentration. So the chances are 0 that we're going to not see phosphorus being produced at the water table. Yeah, Mark?
So Keith, the prairies there, they're not having any fertilizer added to them. So how do these kilograms per hectare, how does that compare with atmospheric temperature?
That's a good question. Anybody else?
In a few places.
Yeah. Do you know?
No, I only know of one study that was done
Yeah. I don't know. I mean, the kilograms per hectare yields that we have here are actually very similar to, we did a study of a dozen different watersheds across Iowa, looking at orthophosphorus and total phosphorus. Those are exactly equivalent to what we saw 12 different watersheds across the state. Again, those yields. So they're not higher and they're not lower. They're like right in the range of all yields everywhere in Iowa.
It was a really clear and well-presented seminar. I want to thank you for that. But I also want to confess that I don't speak the vocabulary, I don't know the vocabulary of groundwater very well. But I want to learn something. So I wonder if you could go to that slide. You had a textural triangle, and you had some contours on it. You were trying to tell us something, but I didn't quite catch it.
Yeah. Let's just do this. Somewhere up in here. I got it. Yeah. We'll just do this now. Yeah, so this one. So everybody here is familiar with the soil texture classes, so that's not, you can tell me a lot about that. So this was work that they did to look at with some modeling efforts, some field verification, how much, what is the apparent specific yield? Not like the total, if you do it on a particle size basis and look at soil pores, these values are going to be a lot higher. This is how much of that specific yield is going to change in the short term, like within a day or two. So I can't remember what the criteria they put on it in their assessment, but in my experience as well, what you see is you see a rainfall, you see the water table jump 3 feet in a day. We're not, that's this conversion of water that was in soil moisture to phreatic groundwater 100% saturation. So this 0.04, whoopsie, might be essentially saying that 96% of that soil profile might be filled with water. We only need 4% essentially added water to cause that jump in the water table. So not sure how clear I'm being, but these values are much lower than what you'd see in a typical soil science textbook because of that. I've done other monitoring where I've come up with similar estimates by looking at a rainfall event based the water level divided by the rainfall event in same units, and you end up with these values that are like 0.05 or 0.06 and so forth, which are on this scale of what's presented here for this readily available specific yield. So it is just like over the span of a couple of days after a rainfall event, this is the amount of soil porosity that you're filling up.
That seems a little bit confusing to me in that I think about from the water table as you go above it, the elevations above it, that the matrix potential is not constant, that it's decreasing as you go above it, and that the air-filled porosity or the drainable porosity would vary with elevation, not just with the texture value.
Yeah.
So that it seems like it's somehow there's a simplification in the assumption.
Oh, totally simplified. So this group is groundwater. I'm groundwater. So yes, this is probably wildly simplistic. Okay, but it gets the job done for us as a groundwater person. So we're going to go with it. So yes, I totally appreciate that. Yes.